Hello there, I'm Tom, and welcome to Newson-Gale's short video on the theory and practice of controlling static electricity as a hazard in FIBC operations. Fire safety is, or at least should be, at the heart of safe bulk product transfer operations using flexible intermediate bulk containers, FIBCs. However, whilst the more immediately visible ignition sources can be taken care of relatively directly, the less visible but no less serious hazard of static electricity could easily be overlooked to potentially disastrous effect. This video gives an overview of static electricity as a hazard to FIBC operations and the practical implications which can help to protect operators and sites and support safer operating procedures. So to begin, what are we going to be covering? We'll start with an overview of the fundamentals. What is static electricity? How does it apply to FIBCs? And why is it important? Next, we'll touch on the research that's gone into the topic and forms the theoretical and empirical basis on which practical insights can be based. From there, we will examine the national and international standards which regulate electrostatic safety in general and for FIBCs in particular. Then, to close out, we'll be looking over practical implications and ways to work towards solutions to mitigate risks relating to this workplace safety issue. Before we jump into that, however, a quick disclaimer. Newson-Gale is an equipment supplier and manufacturer of electrostatic earthing solutions. All images and content shown here are for product information purposes only. The full details of the disclaimer are shown on screen now, and if you have any questions regarding any of this, please contact us or consult our website. Now that's nice and clear, let's move along. Starting then with the fundamentals. This is an FIBC. More specifically, it's a Type C FIBC designed with conductive threads to facilitate electrostatic earthing for use with flammable materials and hazardous area operations. The fact that there is a specific bag designed with the mitigation of the electrostatic hazard in mind shows its importance as a factor in operations, which is reflected in the body of research into the topic, including a series of tests which have given empirical evidence that electrostatic discharge is fully capable of igniting a flammable dust atmosphere arising from FIBC transfer operations. We'll put a pin in that FIBC type question for now, as we will first tackle the question of what electrostatic charge is and how it affects industrial FIBC operations. The short version of this phenomenon is that the movement of materials rubbing against each other, as in the transfer of bulk materials in FIBC operations, generates electrostatic charge, which if allowed to build up, can lead to a discharge in the form of a spark, which can be more than sufficient to ignite the explosive atmosphere. For the longer version, we need to delve into the research at the atomic level. In its most relevant form to the topic at hand, electrostatic charge is a property common to all materials made up of atoms. As the list of things made of atoms includes us and all of the materials which we work with, it's therefore quite prevalent. Under most normal circumstances, materials possess a balance of electrostatic charge, reflecting an equal number of positively charged protons and negatively charged electrons in their atomic structure. During transfer processes, materials move and rub against each other at a macroscopic and atomic level, and at this atomic level, negatively charged electrons can be stripped from one material and retained by another, in a phenomenon known as tribocharging or contact electrification. The exact mechanics of this have been researched in considerably more detail by scientists including Wang and Wang, who produced the diagram shown on screen now. But the practical effect, as far as we're concerned, is that the movement of materials generates an imbalance of electrostatic charge, which, as nature abhors an imbalance, then seeks to rebalance itself. This rebalance can take the form of slow relaxation of charge, or a rapid electrostatic discharge in the form of a spark. Therefore, if this hazard is not controlled, and if charge is allowed to build up and discharge as a spark, an ignition source can be introduced into a flammable or explosive atmosphere, leading to the risk of fire or explosion, causing injury or worse to operators, and the loss of equipment and facilities. As mentioned, this hazard and its consequences have been the subject of a body of research. Concerning the risk of fire and dust explosion, the fire triangle shown on the left should be a familiar sight for anyone working with fire as a safety hazard, with the three elements required for a fire to ignite being fuel, oxygen, and heat. As outlined in research by Amiot and Eckhoff, this can be expanded into a pentagon of factors which can lead to a dust explosion, all of which are relevant to industrial material handling processes, as shown on the right. The first four are readily provided during the transfer of bulk materials, such as filling and emptying FIBCs in industrial processes. Fuel in the form of flammable bulk materials being handled, oxygen from the air surrounding the process, dispersion as the dust or powder becomes suspended in the air, confinement if the process is taking place in an enclosed space, and with the final ingredient, heat for ignition, potentially being provided by an electrostatic spark if this hazard is not controlled. The control of this hazard by preventing the formation of an electrostatic ignition source is therefore critically important in order to mitigate the risk of fire or explosion in these processes. As shown in the tables on screen, the ability of an electrostatic spark to act as an ignition source has been tested and proven. While different materials have been shown to have different minimum ignition energies, the key fact is that if electrostatic charge is allowed to build up on larger pieces of equipment, such as, say, for example, a 1-ton FIBC, the discharge energy from a spark can be more than enough to ignite any of the materials listed, from the relatively volatile sulfur powder to the seemingly innocuous wheat flour. Studies into dust explosions in grain silos, textile plants, and aluminium processing facilities caused by electrostatic discharge show that this is a very real hazard with very real effects, if not controlled. Leading on from this ability of charged items to act as ignition sources, the types of FIBC bags and their usage have also been the subject of research and regulation. Remember that pin we put in the FIBC type question at the beginning? This is that now. As shown in the table on screen, FIBCs fall into the type categories A, B, C, and D. Starting with a simple rule, Type A bags are unsuitable for hazardous area operations in general. While Type B bags are permissible under some conditions with some flammable materials in some hazardous area zones, their inability to be used with all relevant materials and in all zones introduces a large degree of uncertainty for whether or not a Type B bag is safe to use or must be swapped out for another container, adding complexity to operations, costing time to resolve issues, and ultimately reducing the reliability and safety of processes. Meanwhile, with Type D, while an operator may feel they've solved the issue of electrostatic charge by using a Type D bag, it's still necessary to consider electrostatic earthing as a factor in safe operations. To summarise briefly, while a Type D FIBC does not itself need to be earthed, safety standards require that every conductive item within 1 metre of any FIBC, including Type D, during hazardous area operations, does. As Smallwood's research highlights, this includes fixed process equipment situated nearby, as well as personnel and small items such as hand tools brought close to the bag during operations. In addition, possible contamination of the Type D bag's surface can become an issue, as the presence of grease or other substances can interfere with the bag's ability to safely dissipate electrostatic charge via corona discharge into the surrounding atmosphere. This ability to dissipate electrostatic charge without a dedicated earthing or monitoring connection also places a larger responsibility on the operator to conduct quality control checks and ensure correct functionality separately from the bag's operation. The suitability of Type D or C FIBCs for hazardous area operations is to be determined by operators and their risk assessments, but for our purposes, with the simple, direct earthing requirements on the bag itself, we will focus on Type C FIBCs going forward. Bringing this research into dust explosions, electrostatic discharge, ignition energies, and FIBC types together, a series of experiments carried out by Abadot and Cartwright show the implications for real-world operations. Testing under laboratory conditions, it was found that electrostatic charge, if allowed to accumulate and discharge as a spark, was consistently sufficient to ignite flammable atmospheres in FIBCs without conductive threads, and Type C bags with conductive threads, but without a connection to an earth point in place. When, however, the Type C bags were reliably connected to an earth point, no ignitions occurred across multiple tests. We can see the significance of this in the bolded and underlined text in the paper's conclusions, shown here on screen. The question of what constitutes a reliable connection to Earth is examined in research by Yamaguma et al. When subjecting Type C FIBCs to streaming currents up to what is described as an unreasonably high 30 microamps, higher than what would generally be produced from bulk material transfer, a connection to a local earth point with a resistance of slightly lower than 1 × 10 to the power of 8 ohms, that's 100 megohms, was found to be sufficient to prevent the accumulation of electrostatic charge on the bag. Building on the theoretical and empirical research, There are a number of national and international standards and best practices which put these concepts into practice for hazardous area operations in general and FIBCs in particular. As shown on screen, the most relevant of these to today's topic are the ATEX Workplace Safety Directive, that's Directive 1999/92/EC, IEC TS 60079-32-1, IEC 61340-4-4, and NFPA 77. We'll now go through each of these in turn. Starting with the general provisions of the ATEX Workplace Safety Directive for operators in Europe, an obligation is set out to provide the prevention of the formation of explosive atmospheres in the first place, the avoidance of the ignition of explosive atmospheres, and the mitigation of detrimental effects of an explosion so as to ensure the health and safety of workers. While this covers a range of workplace safety requirements, it's the second of these points which is most relevant to our case, with the avoidance of allowing electrostatic discharge to become an ignition source in explosive atmospheres. Moving on from this general provision to a more specific application for FIBCs, the International Technical Specification IEC TS 60079-32-1 sets out guidance for controlling electrostatic hazards, including a specific requirement that Type C FIBCs are designed to be connected to Earth during filling and emptying operations. Completing the set of guidance, the international standard IEC 61340-4-4 and US Recommended Practice NFPA 77 both stipulate that in order to check that a reliable connection to an earth point sufficient to prevent the accumulation of electrostatic charge is in place, a monitored connection for a Type C FIBC is to be maintained to a maximum resistance value of 1 × 10 to the power of 8 ohms, that's 100 megohms, a value based on research by Yamaguma et al. Putting this together then, what practical solutions can be put forward from the research, standards, and recommended practice reviewed here? The first point is a basic principle of safety. The appropriate equipment should be used for the appropriate purpose, which in this case means Type C FIBCs and equipment certified for installation and use in hazardous areas. With the use of a Type C FIBC, an appropriate electrostatic earthing connection is required, which can take the form of a passive or active earthing solution. Beginning with a passive solution, a simple connection can be made with an earthing clamp to one of the designated earthing tabs of a Type C FIBC, connecting to a designated earthing point on site via a cable. While this connection would, at least assuming there are no complications, fulfill the requirement of IEC TS 60079-32-1 to have an earthing connection for the FIBC before and during operations, there are some limitations to consider. The simple connection uses a single point of contact and must be visually inspected to confirm that the clamp and cable are in place. Because the passive solution uses this single point of contact, if a section of the bag's material were to be isolated from that contact point, a risk identified from the testing mentioned previously, there would be no way to tell if this were the case. The connection would not indicate to the operator or allow an automatic response in the event of the connection being disrupted, beyond the operator visually checking the clamp remains attached to the bag. Finally, even with a reliable passive connection in place, the requirement of IEC 61340-4-4 and NFPA 77 for the connection to be and remain below the stipulated resistance level of 1 × 10 to the power of 8 ohm, 100 megohm, cannot be confirmed, as electrical continuity and resistance cannot be verified with a Mark I eyeball during operation. A passive earthing solution of this kind might therefore be better than nothing, but can be improved upon for safety, reliability, and ease of operation. An active electrostatic earthing solution achieves this by taking the benefits of a passive solution and improving on them. An active solution can provide a monitored earthing connection between the Type C FIBC and a verified earthing point on site. In the model shown here, 2 clamp and cable connections are used to run an intrinsically safe monitoring signal out from the system enclosure, which is connected to a verified earthing point on site, via the first clamp and cable through one tab at the bottom of the bag, across the material of the bag itself, then out via the second tab at the top of the bag, via a second clamp and cable back to the verified site earthing point, closing the loop and establishing a continuous monitoring circuit. This therefore provides additional protection against the possibility of parts of a bag's material being isolated from a single connection point. When the system detects that the monitoring circuit is closed and below the monitored resistance threshold, a visual indication can be given to the operator as the system goes permissive.
An active earthing solution such as this can also use output contacts in order to interlock with process equipment, giving additional visual or audible indication when a good connection is made, and allowing for measures such as an automatic shut-off in the event that the connection is disrupted. Such a system is best installed locally to the process, meaning that the appropriate hazardous area certification for the system and its monitoring circuit under ATEX, CSA, CCC, KCS in Metro, IECX, and so on would of course be needed. With this, the active electrostatic earthing solution is able to confirm conformance to the ATEX Workplace Directive and IEC TS 60079-32-1 by verifying that an earthing connection is in place, and also confirms conformance to IEC 61340-4-4 and NFPA 77 if the resistance level to which it monitors is 1 × 10 to the power of 8 ohm, 100 megohm. An active electrostatic earthing solution such as this would therefore fulfill the requirements of the relevant standards and industry best practice, mitigate the risks arising from the topics in the body of research outlined previously, and represent the best protection for FIBC operations, the sites where they take place, and the operators undertaking them. So, to round out, what are the key points to take away from this presentation? Firstly, it's been shown through research into the topic that static electricity is a potential hazard in FIBC transfer operations that must be taken into account and controlled. Secondly, these considerations are not just theoretical concepts, but entail practical requirements backed by safety standards and best practice to support safe operation. And conversely, a failure to take action and control this hazard would mean accepting a risk with serious safety consequences. Thirdly, these practical considerations are best addressed with the use of an electrostatic earthing solution to mitigate the risk, with a passive solution having some limited utility, and an active monitoring system which conforms to the requirements of the standards and best practice being a more comprehensive and safer solution. Would you like to know more? Further reading can be found in the sources used in this presentation, shown on screen now.
And with that, we're finished. If any of this has sparked further interest in the topic, a range of information is available on Newsongale's website and Knowledge Hub, with the new edition of the Electrostatic Grounding and Bonding Handbook now available to access online for free. For specific applications and solutions, our sales team are at your disposal for assistance with answering questions, discussing application details, and tailoring an electrostatic earthing solution to your requirements as needed. Thank you very much, and stay safe out there.